Hello. Today we're going to talk about the Doppler effect. I want to give you a conceptual idea of what the Doppler effect is, how it works. In a later video, you'll go through problems and how to actually do the calculations. Okay. But we want to try to make sure we have a good conceptual understanding of what's going to go on. As you go through this, you're going to be asked to pause the video and do some sketches, and then we'll see how your sketches compare to my sketches. I'm going to use some tools to draw mine to be a little bit more precise, and when you get to the next video and you do the math, you can actually come back and look at my drawings and see, do they match up with the numbers? But right now we're just going to focus on doing some drawings. Okay, now make sure we understand the Doppler effect. Some of you may be familiar with the Doppler effect or how it's used. It's actually got a tremendous amount of applications in our culture. I mean, it starts as a child and you think, well, what sound does a car make when a race car, and you go, Neo! And that's actually a great representation of the Doppler effect. So as a small child, kids understand this concept and they can represent it. So what's going on with the Doppler effect? You have a change in the observed frequency and the wavelength as something moves relative, as a source moves relative to an observer. It's not about the amplitude. Yes, when the car gets closer to you, it does get louder, and as it moves away, it gets quieter, but that's not the Doppler effect. The Doppler effect is specifically looking at the frequency and the wavelength. How are those changing as a source and observer are in relative motion? Okay. Other applications, you have Doppler weather. A lot of our radar for weather is based on the Doppler effect and how the rain is moving relative to the sensor, and it can tell you how fast the rain is. A radar gun, if you've ever gotten a speeding ticket, chances are most speeding tickets you get them by a police officer using a radar gun, which uses the Doppler effect to show how fast you're moving. If you're in medicine, you might use the Doppler effect with echocardiogram, with ultrasounds to measure the flow of blood, how it's moving in your body. Okay, and the whole idea of the Big Bang theory, not the show, but the actual theory, the very beginning of that premise, it comes from the Doppler effect applied to light and how stars appear. And therefore we get a sense of their relative motion. So there's a tremendous amount of application. So it's kind of helpful if we know what's going on here. So right now I want you to visualize, and I want you to draw something for me. I want you to pretend that this white sheet that I have in front of me is a pool of water. You're looking down straight on top of it. It's a calm pool of water. And you're going to take your finger and you're going to touch the water once every second with a frequency of 1 hertz. 1001, touch, touch. What would you have? So just pause the video now and draw what that would look like. Now, I'm going to use some tools to draw this, and what we should end up with is we want to think about, well, the most recent wave that would have been made would be just a dot. So I'm going to put a dot here. Okay, so the first dot, the last, shall we say, the last wave is but a dot, okay? And it can be a collection of waves. They are each made 1 second apart. The period would be 1 second. The frequency is 1 hertz. And so the age of the next oldest wave would be 1 second. If the youngest one is but a dot, the next oldest one is 1 second old, and they go out and they form a circle. And if it's been going for traveling at 2 centimeters per second, that's the speed of the wave. Okay, now the source is not moving. The hand is just staying in the same location, making dot after dot. The waves would have grown and would after 1 second would be 2 centimeters in radius in all directions. So it'd give you a circle. Okay. Now the next oldest siblings, think of these as a family of circles, would be 2 seconds old, and traveling at 2 centimeters per second, a wave that is 2 seconds old would have a radius of 4 centimeters. And the next oldest one, being 3 seconds old, would have a radius of 6 centimeters. And the last one, being 4 seconds old, would have a radius of 8 centimeters, and therefore would have a circle like such. Okay. Now, let's say that we put some different people in this pond. Let's say we're going to put Cindy over here and Omar over here on the left. As these waves come to Cindy and Omar, they will get hit once every second. A wave will hit them once every second. They would measure the frequency as 1 hertz. And if they were to pull out their ruler, they would say, oh, the ruler, I can measure the wavelength. This distance here would be the wavelength. And we see, oh, the wavelength is 2 centimeters. So they get the wavelength of 2 centimeters and a frequency of 1 hertz. And we know that the velocity is the frequency times the wavelength. 2 times 1 would simply be 2 centimeters per second. And we know that's the case because that's the speed of the wave, 2 centimeters per second. Cindy would measure that. Omar would measure the exact same thing. Okay, they're not moving, and the source is not moving. Everyone's sitting still. The only thing that's moving are the waves. Okay, now let's take a look at the next scenario. This next scenario, almost everything's the same. The frequency is still 1 hertz. The speed of the wave, the speed of the water wave would be 2 centimeters per second. But now the source, your hand, is going to be moving to the right at 1 centimeter per second. 1 centimeter per second. Okay, so now I want you to pause the video and I want you to sketch what this picture is going to look like, where your finger still touches the water once every second, but now your hand is going to be moving to the right. So pause the video and draw that. Now, here's how we would actually draw it. We think of this, say, well, where is the newest wave? Well, it's just a dot. I'm going to put a dot here. That represents the youngest wave just being made. Well, how old is this next oldest sibling? Well, it would be 1 second old, okay? But it wasn't born at the same location. So you think about it, some of you may come with families where you were born in a certain community, but your younger or older siblings may have been born at a different community because your family moved during the time when kids were being born. And so you might say, oh, I was born in this community. One of my siblings was born in a different community. Same thing here. This wave, which is a dot, was made right there. But its next oldest sibling, so to speak, was made 1 centimeter to the left. How do I know it was made 1 centimeter to the left? Because the source is moving to the right at 1 centimeter per second. So 1 second ago, the source must have been 1 centimeter to the left of the present dot. But the radius, just like we did before, the radius is 2 centimeters. If I get that to be exactly 2. I draw the circle. Now, the next oldest sibling would be 1 centimeter to the left of that. So we're going to draw 4 of these. Okay, so the next one is centered here, and it has a radius of 4 centimeters. There's this. The next one is here. It has a radius, it's been around 3, so it's going to be 6 centimeters. We'll draw one more. That would be 8 centimeters. Bring it around. Okay. Now, you'll notice these are bunched up here. The wavelength here on the right is small wavelength. The wavelength on the left is big. Okay, so now let's put Cindy back here, and let's put Omar over there. What do they experience? Well, Cindy is going to get hit by waves that are coming with a wavelength of only 1 centimeter. Where if you look in the ruler over here, Omar would measure these to be a wavelength of 3 centimeters. Okay. Now, the product of the frequency and the wavelength still always has to be the 2 centimeters per second. Frequency and wavelength don't determine the speed of the wave. That's determined by the medium. The medium hasn't changed. So you realize that, oh, the frequency here must be 2 hertz. Cindy's getting hit by waves twice as often. Okay, but over here, the frequency for Omar would be 2/3 hertz. Because 3 times 2/3 would still be 2 centimeters per second. Okay, so that's going to be the frequency for Omar, where the frequency for Cindy, she has a higher frequency. Okay, so now, but let's say the source, we could say it's your finger making waves, but this could be a jet airplane on the runway, or it's on the runway and it's moving to the right. And as it moves to the right, could be a car blowing its horn and sound coming out with a certain frequency, but Cindy hears a higher frequency than Omar does. Now, as the plane or the car or the train goes past Cindy, Cindy will eventually be to the left of the source and experience exactly what Omar experiences now. So as it goes past her, it will start with a high frequency and eventually transition to a lower frequency. Now, common mistakes. If you drew this and use, I typically see a lot of students who will draw waves that look like this. Okay, and so give you a helpful hint. If you drew circles, if your drawing had circles, any of them were the same size, that means they were the same age. That means they were born, created at the same time, but if you can see them, they look different. They were created at different locations. Okay. Yes, it's true that these waves that I've drawn were created at different locations as my hand moved. However, they're all different sizes. So as long as you're always making one wave at a time, only using one finger to make these waves, all your waves will always be different sizes. Okay. Now let's go to the next scenario. There's going to be 4 drawings we're going to do. This next drawing, what we have is everything's the same, except now the source is moving to the right at 2 centimeters per second. That means if the youngest wave is here, its next oldest sibling was born there, the next one was born here, there, and they're all 2 centimeters apart. Okay, so now pause the video, draw what you think it's going to look like. It's going to be similar to the last one, but the key thing is this number 2 matches that number 2. And that's going to be significant in your drawing. So see if you can do a quick little sketch. Okay, so now let me draw it. So first one, the last one to be born is just a mere dot. Its next oldest sibling was born 2 centimeters to the left and is 1 second old. So it would have a radius, which is, let's see if I can get this to open up, 2 centimeters. Its next oldest sibling is 2 seconds old. It was born 4 centimeters to the left. It has a radius of 4 centimeters. Next one is 3 seconds old. Born 6 centimeters to the left, has a radius of 6 centimeters. And the last one was 4 seconds old, born 8 centimeters to the left, and has an 8 centimeter radius. Okay, so what we see here, let's see if I can get rid of that straight line. Let's put Cindy here and put Omar and see what do they experience. Well, what you'll realize is that Cindy doesn't get individual waves. okay, she is getting all this energy. Remember, waves are a form of transferring energy. She gets all this energy all at once. And this is crest on crest on crest. So we have a tremendous amount of constructive interference. A lot of energy is located at this location. Okay. Now, Omar is going to see waves which are pretty darn big. Okay. Wavelength of like 4 centimeters. 4 centimeters is the wavelength he experiences. Okay. 4 centimeters for the wavelength here, where Cindy doesn't have a wavelength and doesn't have a frequency, because hits by a pulse. That would be, in this case, if this is a wave, the source is traveling at the same speed as the wave. If this was a jet airplane, the jet would be traveling at the speed of sound. Be traveling not subsonic, which was the previous one, below the speed of sound, but at the speed of sound. As a result, this would be a sonic boom. Cindy would get all this energy all at once. Okay. Now, our next drawing, or our last drawing, is going to be where the speed of the source is greater than the speed of the wave. Okay, so now think about what that's going to be. Stop the video, sketch how you think it's going to look. Now, I'm going to draw it, and this is going to be representing a plane which could be flying faster than the speed of the wave, or supersonic. Okay, so I'm going to say the youngest wave is about a dot. Next oldest sibling, born 1 second ago, was born 3 centimeters to the left. Next oldest one, 3 more centimeters to the left. Then 3 more centimeters to the left, and then 3 more. Okay, so the first one, the youngest one is a dot. The next oldest one is 2 centimeter radius. Next one here would be a 4 centimeter radius. Next one will be a 6 centimeter radius. And the last one will be an 8 centimeter radius. All right. So now, what we get, we put Cindy here, we put Omar over here, and we see that Omar gets hit with these big, large wavelength, low frequency, doesn't get hit very often. But here's what's interesting. This here, the region of constructive interference, is along this line. Along that line, the region of constructive interference. Now, I've drawn this picture in 2 dimensions, but I drew circles. In real life, these are spheres. And this isn't just an angle here, this is a cone. Okay, this is a cone. And what you have is you have something which is traveling supersonic, okay, faster than the speed of the wave. Now, if you've been skiing, you might recognize this diagram. This is a wake, okay? And skiers, if you've ever been water skiing, you usually start out in the wake, and there's a little bit of disturbance here inside between the wake in there. However, sometimes skiers will try to get outside the wake, come out here, where it can be really smooth. If the rest of the lake is really smooth, this part can be smooth out here. Okay, but this region, if you've been water skiing, you know what this is. This region here, there's a lot of energy there. That's like a hill of water. It's like can be a foot or 2 tall. In fact, wakeboarders will use that big hump of water as a ramp. That's constructive interference. Okay, now, so what we get is we get a case of going supersonic. You're producing a wake. And for the pilot, it can be very calm out here. Now, what's interesting, let's pretend I'm running from left to right, okay? And as I run, each of these circles will represent me counting. So I count 1, 2, 3, 4. And the first circle I drew, which is the biggest one, I would label that as 1. And then the next one, next smaller, is 2, and then we get 3, and then we get 4. Okay, and then the last dot would be the 5th one. Okay, if we go back to the previous ones, okay, let's say here, and the oldest one, we'll call that 1, 2, 3, 4, and the youngest one being made would be the 5th one. Cindy gets hit by wave 1 first, then wave 2, then wave 3, then wave 4. If I was running from left to right and I yelled out 1, 2, 3, 4, Cindy would hear 1, 2, 3, 4. But in this scenario, which wave is going to get to Cindy first? Well, it's going to be wave 4, and then 3, and then 2, and then 1. So she wouldn't hear 1, 2, 3, 4. She would hear 4, 3, 2, 1. Well, orf, eat, and oot, and own. So it would be, the words would actually sound backwards as well. That's a case of if I could run faster than the speed of sound and call those out in those intervals, she would get the information in reverse order. Now, she also would not hear me coming because, unlike in this scenario here, I am arriving after my sound arrives. Sound gets to her first, she hears me coming. I come after the sound. But in a supersonic situation, the plane, let's say it's a plane, gets to a place before its own sound gets there. You'd never hear the plane coming. Okay. Now, what's interesting, if you want to talk about light, let's say I could theoretically go faster than the speed of light. If I could go faster than the speed of light, Cindy wouldn't see me arrive. I would just appear there immediately because I get there before the light traveling, and then she sees me travel in reverse order. And any light that bounced off of me at 4 would get to her before 3, get 2, and then 1. So as I run towards her at greater than the speed of light, she doesn't see me coming. All of a sudden I appear, and then she sees me run backwards, both to the left, and sees me run forward to the right as these waves continue on. Okay, so this is the Doppler effect. Hopefully you've drawn some sketches that kind of match up with these. And I'm going to show you some of the mathematics of that in the next video.